Presented by Caltech.
This course, at least on its face, might seem pretty boring and might seem pretty bland. It's just about oscillations and waves and simple harmonic motion. But the concepts which bind it together are very, very universal. Things like Fourier decompositions, things like how do you get the equations of motion. There is a harmony to the whole thing. And I'll try to convince you that we might have learned Snell's law or laws of reflection from drawing out paths of light rays, pick a bunch of things, but it can be all traced back to a much more deep-rooted idea in physics. And no one really knows why it works, I think, but it does work. And once we have that discussed, I'd also talk about how Fourier decompositions, which I have mentioned a few applications around the way, but this time I try and connect it back with the very fabric of space and time in a certain sense. That nature itself has this intrinsic inbuilt uncertainty, which it's not that you cannot measure things accurately. Nature doesn't allow you to do that. And that is tied into the idea of Fourier decompositions. So we talked about that a little bit. And towards the end, hopefully we'll have time enough, I got a disk and stuff. And I printed one of these protractors out, and I also got a laser. So we'll try and shine laser light on the disk, and we'll try and measure the storage capacity to see how our basic ideas of the Young's double-slit experiment and diffraction, how they work out in detail. But again, I have no big agenda. If something interests you a little more than the other topic, ask me. I'll stop there. I'll discuss more about it. I just wanted it to be more about taking a breather and just enjoying the bigger picture today. I know that people get lost in homeworks. We rush you a lot around here, so today is super easy. Right? So just ask me anything you want, and we'll see what it goes. Okay. So I want to talk about that principle which basically binds all of physics together. And it's the principle of so-called least action. If I was more true to what I'm saying, it should be called the principle of stationary action, but we call it the least action for conventional, historical, and other purposes. And let me first let's get back to what we know about nature so far. Like Newton's laws, right? A single particle in one dimension. What do we know about it? Its force equation, mx double dot f of x. You specify all the forces, you can find the acceleration, you know what the particle is doing. You solve for this, and you can find the trajectory, x as a function of time. And how do you do it? You specify initial conditions. You have the force law, and someone tells you what the position is at x equals 0, and the speed is, or the velocity is, at x equals 0. And the beauty of this law, or rather of most differential equations, is that it's a local law. Most of physics is local. By that I mean, what happens to something, to a system, only depends on its current state. So for this differential equation, if I know where I'm at, x at some time, and I know where I'm going, the velocity, I know where I'll be next. I can solve this equation, I can find my x and x dot at the next instant of time. I take that as my initial position. I again say, I know where I am, and I know where I'm going, I know where I'll be next. Okay? So it's all local. Where I start determines where I end up. And that's how physics really operates. It could have been more bizarre. To be honest, more recently over the last, couple of decades, we found this inclination that the fact that gravity might be non-local. I mean, we know it's non-local in a certain sense, but that non-locality might be much more drastic than we thought it previously was. It might be so drastic that in the presence of gravity, you can't even understand how you could localize information in a region of space, which is very counterintuitive. Like gravity should define space itself, but if there were gravity, and you try and localize some information in that region, like quantum mechanically maybe, it doesn't work out. So there are hints of non-locality, but for the last, 500 years, physics has been thought to be mostly local. That's how it basically works. Let's say equations for electromagnetic radiation, light. So you have the electric field, so you have partial squared E, partial T squared, there's the speed squared, the Laplacian acting on the electric field. Again, it's a second order differential equation. If you know what the electric field is, that's you. If you know what the E field is at a certain location at a certain time and how it's changing, you can work from there. Okay, it's a local law of physics again. And it's another interesting, deeper idea that why do our laws of physics have second derivatives in them? More often than not. You would hardly find a third derivative in them. You could maybe have a first, like in Schrödinger's equation that we talk about next term, if you take quantum mechanics, but it's mostly second derivatives, x double dots, second spatial derivative, and so on and so forth. This also ties back into the fact that the energy of a particle, the kinetic energy, is momentum squared. It's a second power, not some other arbitrary high power. And it all connects back. If you have higher powers of momentum, momentum is able to translate position. So if you have momentum, it can move things around, heuristically speaking. So higher powers of momentum make you move in more non-local ways. And the second power, which I'll talk about this in a little more detail at the end of the day, but the second power makes you move in a very localized way. So the fact that we have double derivatives, we have second powers of momenta, they're all like intertwined. And honestly, no one really knows why the design is as such, but it's like that. Okay. So we know how locally nature works. Turns out, nature is even more interesting than just being a local law of physics. Nature also obeys a global constraint on what things can do. And that's the principle of least action, which at its heart says that if I know where a particle or some system is going to be at some time, initial time, at this time, just its location, let's say, and I know where it's going to end up after some other time. I know the start and the end, not just the start. If I fix the boundary conditions, you can uniquely, or almost uniquely in some senses, find which path that particle will take, such that it minimizes a so-called action. Nature is lazy in that sense. It wants to go from point A to point B in the least way of resistance, if you may. It probably sounds the best way to say it out loud, but it tries and follows a path which minimizes the action that is given by where you start and where you end up at. Okay? So we'll see how this works in a little more detail. So the action, typically, it's called by S, it depends on what path you choose. Okay? So let me call this a slight change of notation, but this depends on the trajectory of the particle, not where the particle is at this moment, what net path it will choose to go from point A to point B, which are fixed points. Okay? So the action depends on paths. It's not a function of a single variable, it's a function of a path itself. For each path, it gives you a value. It's a machine like that. Okay? So if I say that the particle must start at point A and must end at point B, we don't know what it's going to do. All I'm saying, it starts here, it ends here. It could take any possible path. It could go in a straight line. It could curve around. It could curve like that. It could go to the sun, come back. It could do anything it wants to do. And the principle tells us that it will choose that path for the given configuration such that that path has to minimize the action. How on earth does the particle know which path will minimize the action? I don't think anybody understands that fact. But there's like a global understanding to how this whole thing works. And because of which you can derive everything that we know about physics so far from this principle of least action. You can derive Newton's laws. You can derive EM radiation. You can derive Einstein's gravity. You can derive quantum field theory. You can derive thermodynamics in a certain sense. You can derive string theory, it all arises from an action principle. Minimization, or demanding it's stationary, it doesn't change to first order, that's what gives you the actual laws of physics in the universe. Why is that? I don't know. But it's interesting that nature obeys a more global understanding of where you start and where you end up. It'll fix the path for you. Okay. Or you could go in a more local way. And they're equivalent as far as we understand. Let me give you an example of how this works. We all like the laws of reflection. And if I have a mirror, or if I have some reflecting surface, if I shine light, it hits the point, reflects off the angle of incidence, the angle of reflection, the whole high school story, and even physics two-way story. Let's see how we can connect that back with the principle of extraction. So say I have a mirror or something, reflecting surface, and I start at point A, for example. Again, I have to fix my starting point and my final point. And let's say I fix my point B. I want light to get from point A to point B by reflecting on the surface. That's my constraint. I could, of course, have a light ray going from A to B, that's fine, but I want to understand how reflection works, and hence, I want to see how light can go from A to B by bouncing off this surface. Okay. We don't know what path it will take. I don't know the laws of reflection so far. Okay. Turns out, the principle of least action can be reformulated into what Fermat, back in the day, called the principle of least time. So that thing gets rewritten in terms of the principle of least time. This is Fermat. I think it's Fermat. I think it's Fermat. That's how you pronounce the name? I'm not sure. So the Fermat principle. I'll use that name for now. And the fact that we don't know what the path is, but the path that nature will choose is the one which will minimize the time taken from A to point B via the mirror. And its minimization is actually stationary action for that path. Let's see how that works. So let's say I travel around. I choose some path, arbitrary. So let's say I go from here and then reflect off like that. Okay? This way, this angle at theta 1, angle theta 2, they are generally different. I am fixing my initial and final points. Hence, I'm thinking of this as this height at which A is h1. The height of B is h2 from this level. And I'm fixing h1 and h2. And I'm also fixing how far these 2 points are, L. Okay. So I fix these 2 points, and I'm asking the question, which path light must take, such that it minimizes the time. So how do I characterize these paths? Let me call the distance where it hits the mirror a distance x from the point of A's projection. And then therefore this distance is L minus x. All okay with that? Ask me questions. I mean, there's no constraints here, so keep bugging me if you want. But is this okay, everyone? All right. How much is the total time taken? I'd like to go from A, hit the point P, where P can vary. So I can vary the point of reflection, by which I mean I can vary x, this location. And this is what I'm saying by varying all paths. For different choices of the path, I can find different x's by which light reflects. Okay. I'm making some assumption here that, okay, in free space, light travels in a straight line. That can also be proven by the principle of least action, but we take that for granted for now. And we just like find what happens at the reflecting surface. So what's the time taken now? How much distance is it traveling from A to point B? Root x squared plus h1 squared. Okay, that's the distance it travels from A to point B, divided by the speed of light c. To get from P to B, how much distance? Same thing, L minus x, the horizontal length, plus h2 squared Oops. All okay with that? And this t depends on x, and this x is a representative of which path I chose to go from point A to point B. Okay. Now, the real path that light will take is the one in which it minimizes the amount of time taken, and therefore the first derivative has to vanish. Let's see how much that is. Let's differentiate this. So 1 over c from here, square root, so it's 1/2, square root goes down, h1 squared plus x squared. What happens on top? 2x plus 1 over c square root and minus x whole square plus h2 squared times 2 times minus x. That look okay? Alright. And this must equal 0. I can cancel the 2's. I can, there's a 2 here as well from the square root. I can cancel the c's off, and what do I have? Sorry, this should have been, let me call this way, twice L minus x times a minus sign. That sounds right? Yes, sorry, my bad. This sounds right now. So I move it around, and what do I have? I have x over square root h1 squared plus x squared equals L minus x over square root L minus x whole square plus h2 squared. That looks horrible, but what is x over square root h1 squared plus x squared? What's x over square root h1 squared plus x squared? Cosine or sine? Sine. Sine theta 1 equals la-di-da L minus x divided by this hypotenuse. We just derived the law of reflection by the principle of least action, the principle of least time. Okay. Similarly, if I wanted to do refraction, I can do the same thing. I can take a boundary. I can take a point A at some height h1, my final point B at some height h2. I fix the length between them, so therefore the points are now fixed. I can choose any path, labeled again by x, let's say, like this. I can call this angle θ1, this angle θ2. What's the total time taken now? To go from A to point B, the same thing. It's square root h1 squared plus x squared divided by what? If I say that this medium 1 has a factor index n1, this is n2. What's the speed in medium 1? C over n1, right? C is speed of light in vacuum, medium of factor index n, therefore the speed is just c over n1 plus square root L minus x whole square plus h2 square over c over n2. Run the same argument. I just have additional n1s and n2s. What you find is n1 sine theta 1 equals n2. So I could have done the whole same thing with, some Huygens principle of wavelets and light travels and this and that and all that, but just by the basic idea that there is a principle of least action, which for light means a principle of least time. There's also a connection for that. I won't discuss that today, but it can be shown. Just by demanding that you vary over all possible paths. You can go this, like that, like this, like that, but the one in which it really takes the path is the one in which minimizes time. So now you know if someone is drowning in water and you're on the beach, you got to save them, there is an optimal path that you can choose. Because you're faster on land, I hope, I guess, than in water. So you can find which path takes the shortest amount of time and you get to that person. So it has more applications than you can do. Make sense? Seems interesting a bit. I could do like much more, but I will give you like a flavor And then you add over all paths, and then you see which one is like the interesting one. All of quantum mechanics can be framed in terms of the least action principle. There you have something called the partition function, where you sum over all possible paths, point A to point B, take every path you can think of, infinite number of them. This one, around me, above me, from the sun, Andromeda, every possible path. And every path has a weight, a weightage. And that weightage is given by the action. Okay, there's a whole way to think about this. But I'll just close this discussion by pointing out that for Newton's laws, like one-dimensional regular things, the action has the following form. The action is integral dt from point 1 to point 2, initial time to final time, times something called the Lagrangian. The Lagrangian is nothing fancy, at least here. It's just integral dt from what you have, t2. The Lagrangian is just the kinetic energy minus the potential energy. Not plus, minus. K plus V is the energy of the mechanical particle. K minus V is the Lagrangian. So this is just integral dt from t1 to t2, 1/2 mx dot square minus e of x. You apply the principle of least action. You demand that the action is minimized. So this del is variation of s by changing paths. You change a path, you find the corresponding action, and you demand that at the correct classical path, the action variation is 0 to first order. And when you work this out, I think I don't have enough time, but what you find mx double dot equals minus it's built into that. All of relativity can be derived from a similar action principle. All of gravitation, there's an action called the Einstein-Hilbert action, and you just differentiate that, you demand its 0 change to first order, and you find the equations in motion. So inbuilt into this character is a local law of physics, but globally it's also encoded in how nature really works. Let me talk about something even more bizarre, and I guess even more bizarre than this. Remember Fourier transforms, our best friends? Yeah, they are literally our best friends. I read an article like a couple years ago, maybe in the Guardian or something. It said Fourier transformations, something which lets you bake and eat your cake at the same time. You can do both. Anyways, so for Fourier transformations, remember how we said any arbitrary solution for oscillation is a sum of normal modes, right? So this schematically is a sum of normal modes. And normal modes of vibrations and waves are sines and cosines. And we had something like sum over n. Remember the general formula, an cos knx plus dn sine knx times cn cos omega nt plus dn sine omega nt. Remember that? The generic Fourier decomposition. Don't worry, I'm not going to make you solve for this for a string or something today. That's not the point. But that's the decomposition that we have. Okay? And remember, we found these n's to be discretized because of boundary conditions. Fixed, 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 open, open, open. The wave starts from rest, whatnot. That fixes these constants and the fact that the k's and omegas are quantized, or they're discrete. Okay? So the discrete index was from some boundary conditions. Now say, just for the general case, like imagine there are no boundary conditions. Okay? It's just all possible normal modes. And normal modes were labeled by the frequency of that mode, right? Out here, omega n was v times kn. So I can just label each by n, which tells you what the frequency is. So I'm basically summing over all possible normal mode frequencies, their solutions. Okay? In general, if there were no restrictions on my boundary conditions, I could have written down psi xt not as let's say, a discrete sum, but a continuous sum of omegas. Omegas won't get discretized then. Okay? So how about I fix a location in space, let's say at x equals 0, for example. So my oscillation at that point, I'm seeing how it changes in time. So I'm looking at psi 0 comma t, which I'm just going to call psi of t for convenience. Okay. And I'm summing over all possible normal modes, which means I am summing over, integrating over all possible frequencies now. It's a continuous transformation. So I'm summing over all possible frequencies. And the normal mode looks like e to the I omega t. That's the oscillation part, correspondence of this piece, times the amplitude of that frequency term, which was this, depending on which normal mode you chose, which end. But now you have a continuous spectrum. So let me call this psi tilde omega. So that's the amplitude of the normal mode of frequency n. This is the normal mode itself. Okay? And if I'm a good person, I'll put a 1 over square root 2 pi, because the world demands me to do that. It's convention. You can also not do that, but let's do it for now. Okay. So for continuous sum of frequencies, you can decompose any signal into a continuum sum of its normal modes. And this is the famous Fourier transformation. What we discussed in class was the Fourier series. It's a series over discrete ends. This is the transformation in a continuous function space. Sometimes. Yeah. Yeah, the weather is weird. I have a road trip planned right after this class to Utah, and I have no idea what the weather's going to be like, so there might be snow and stuff. Yeah, that's nice. Okay, and the beauty is that this thing can be inverted to find psi tilde of omega. Remember how you found A's and B's by Fourier's inversion trick? You took this part on the other side and dated it out and so on and so forth. You can find psi tilde omega to be 1 over square root 2 pi, again convention how it works out, integral dt. You go to the time variable now, you're summing over, like in the string case, it was integrating over x now. In this time, you have psi t e to the minus I. Given a signal, I can find its Fourier components. Given a signal, I can decompose it into its Fourier components. Okay? And this inversion is so-called the Plancher's theorem. You don't bother with this for now. I'll make you bother about this next term in quantum mechanics a lot. So we can take it easy today. Next term, we will not let you take it easy on that stuff. Okay? That's Fourier transformations. What does that say about something? What's the Fourier decomposition of sine omega t? That's my psi of t. Which omega contributes? Or let me call this sine omega naught t, or fixed omega naught. The oscillation in time is just whatever. That's how it goes. That's psi of t. What's its Fourier decomposition? Which omegas contribute? Omega naught. In that sum, only the omega naught contributes, and that's all I have. Okay? So if I want to plot out psi tilde omega as a function of omega, the amplitudes of different Fourier modes, which was ANs or BNs that we had before, but now I have psi tilde, that's the amplitude part. This thing, how does that look like? This is the sine wave, the psi of t. How does psi tilde omega look like? So let's say this is omega naught. Out here, what's the value of psi tilde omega? 0. There's no contribution. Here, 0, 0, 0. The contribution here peaks. One. I will not prove this, but I'll mention to you that, let's say, if my function psi of t looked like this, if it was 0 here, then a rectangular bump, and 0 like that. That's my psi of t as a function of time. And if this width here is, let's say, A, okay, that's psi of t. In the limit A is much, much less than 1, when this width is really, really small. So it's really peaked in time. You know when the signal happens. It's 0, like that. This happens at this instant. Okay. For this really short width limit, the Fourier decomposition, psi tilde omega as a function of omega, guess what? Looks like a straight line across all omegas. And if I have a limit A is much, much larger than 1, so I have a broad signal here in time. The Fourier decomposition then, psi tilde omega, is a sinc function, but it looks like that. Digest that for a moment. Something which was completely delocalized in time. It existed for all time. Its Fourier thing was completely localized. Because only one frequency made it up. Same thing here. If it's completely localized in time, it's completely delocalized in Fourier space. If it's completely a much, much more than one, completely localized in the time domain, it's more localized in the Fourier domain. So there is this conjugate relationship. There is this, synergy between the one domain, the time in this case, and the Fourier domain of that. Things which are limited in one look broad in the other, and vice versa. And why it's vice versa? Because of Plancherel's theorem. Psi tilde omega is the Fourier transform of psi of t. So they just work the same way. There's no distinction between which should I call time, which should I call omega. It's just two variables, and they're conjugates. Do we all see this? Any questions? It's not the most obvious thing for looking at it for the first time, but if you have questions, please ask me. This is interesting, I
think. Is there some kind of physical meaning to the Fourier space?
So, excellent. It depends on what your actual variable is. Like for the case of this sine wave, which is, let's say, in time, these are the frequencies, the harmonics which make it up. You know this music, you know how like these days, now that tech is advanced, we play a song to our phones tell us which song it is. This is what it does. It hears the actual sound, it decomposes it into its Fourier components, and then matches the Fourier component to every song that is known in the library. So this is, in this case, if it's time and real frequency, then it is time and actual frequency of oscillations of individual sine waves. But this could mean more generally, and I'll talk about that. But there's an inverse relationship between the two. And you can decompose any signal into its Fourier parts, and the Fourier parts are easy to analyze sometimes.
Could you go over again why, if you have the function that looks like a box almost, why the psi tilde would be a flat line then?
The question is, if this case, if it's really peaked here, then why is it this way? That's the nature of the transformation. That's what the transformation does. I can yap more about this maybe after class, but the point here being that this inversion takes you from localization in one space to be more broad in the other space, right? So the sine wave is the most delocalized thing. It's everywhere. And that in Fourier space becomes a peak at one point. And these are like more, every function has a Fourier transformation, and not every function, the function has to be square, integrable, and yada, yada. So this condition has to obey and so on and so forth, but that's for next term. It's not that hard, trust me. But the point being that localization in one means more broad and vice versa. Okay? All right. Now I'll say a few words about quantum mechanics. This was time and space, time and Fourier domain. In quantum mechanics, position and momentum are Fourier variables. So if I have a function psi of x, its Fourier decomposition is sum over all momentas, which are labeling my Fourier domain, e to the I px, the corresponding e to the I omega t, times psi tilde p. And these x and p are now really position and momentum. Like how this was time and frequency, this is position and momentum. So if I have a particle, if I have a quantum state, which is, let's say, localized in position, that's its space wave function, it's localized in position, what do you think happens to the momentum of the particle? This is the momentum description of the particle. If it's already peaking position, the momentum part, psi tilde p, is much broad. And what does that say? The state is psi x or corresponding psi tilde p. If I can go and measure, or if I localize a particle really closely in x at a certain point, its possible momentum observations would be really, really spread out. If I go and measure this particle, I will always find it at this point x naught. So I'm pretty certain that it's at x naught with some little variance. But if I go and measure the momentum, one measurement lands me this value. Other measurement gets me this value. Third measurement gets me this value. And the spread in the observable of momentum is huge. And this is inbuilt in nature. It's not that you can't go and measure more precisely. Nature doesn't allow particles to have simultaneous values of position and momentum. It's just not possible. Classical mechanics let you do that. Classically, I gave you x, I gave you x dot, and x dot was just momentum at 0 over the mass. So classically, both the variables exist. Quantum mechanically, it's not that you can't measure them. They don't exist together to be a certain value. And this uncertainty is like interwoven in how nature is formulated. It's not about my device in the lab, it's not about how precise I can be, or if I fudge my readings in the lab. No, it would not work. Nature doesn't allow you to know everything at the same time. That's what quantum mechanics is all about. It's uncertainty, it's probabilities. I mean, it's more than that, to be honest. But this underlying fact is like inbuilt into quantum mechanics. And x and p make up a Fourier pair. And a lot of my own personal research work is focused on how these things work. So if you think about like position, a single particle can have any position, right? Like from negative to positive infinity. It's like infinite possible values. More recently, we have hints from gravity and black holes and stuff that nature can only do finite things in a region. You can't do infinite things. Like this particle can do infinite things. It can be anywhere on the line. But if you think about gravity, you find out that nature can only allow for finite, discrete possibilities. What's the underlying discrete form of x and p? How do they play around? How does that affect quantum mechanics? How does it affect quantum gravity? That's like my own research, whether I'm pushing for right now. But it's all interconnected at a bigger level. Okay. Any questions about this stuff? If you take quantum next term, we will work this out in a lot more detail. We hammer this to death, almost. But that will be really interesting. Again, you'll be caught up in the sets and everything, but I want to remember this and kind of see the bigger bird's eye view on how things are really working. Any questions about this stuff? What with me? Seems interesting, somewhat. Okay. So I have another 7 minutes. Let's quickly try and do some experiment and see if we can run this out. Okay. So the DVD, it stores stuff, right? How it stores stuff? There's the DVD disc. There's a central hole that you have. The DVD has a track which runs in a spiral like that. Okay. And the spiral has these things called pits. Like actual, I don't know what to call it, like pits, that actually literally pits, they kind of make these little things with electrons and so on and so forth, but these pits are what store the information. There's a reflective material, there's some material, when you burn the disk, that disk shines a laser on this, and it burns that part, hence we call it burning a disk, and if it burns it, it puts in a 1 there, like a bit 1, or 0, and that's how it reads information, very broadly speaking. So I made up a simple model for how a disk might work. This spiral thing seems hard. So how about this model for the disk? As a central hole, that's the full disk. I will replace the spiral track by concentric circles, let's say. Okay, just call a sign for that. So let me call this radius of the inner hole as R0, the inner hole of the disk. Let me call the writable part of the disk, where you can actually have the track. So this is the inner hole. From here to the outside, let's say it's D. Okay. So how can I label my concentric circles? So I can label them by R sub I. It starts off little more than R0, I times D. And D is the distance between adjacent tracks. Okay? So out here, I goes from 1 to I max. Okay? Concentric circles. What's I max? I max is the one in which I hit D. Okay? So I max is just capital D over little d. Because when I have that, the radius becomes R0 plus capital D. You all see that? All with me? Okay. That's all right. Okay. Let me say that the distance between these tracks is L. Okay. So how many total pits do I have? A single concentric circle has a circumference 2 pi Ri. The distance between these pits in that track, in that concentric circle, is Li. That's the number of pits in the ith circle, and I sum it over all i's. That is the total number of pits that I have. Is that okay with everyone? Right? Let's sum this up. So L is the constant for all the concentric circles. So I have 2 pi over L, sum from I1 to capital D over little d, times R0 plus I times little d. I'm summing that over. The first term is a constant. R0 gets pulled out, so I have sum over from I1 to this of 1, which is just the maximum value. And this is d over d in the first term. Second term, I'm summing, d is a constant, little d is a constant. I'm summing I from 1 to capital D over little d times I. So I'm 1 plus 2 plus 3 plus 4, so on to this value. What's the arithmetic series of 1 plus 2 plus 3 plus 4 till some final number? Final number n. N into n plus 1 over 2. Right? And d over d is pretty large, typically. So this second term is like n squared, the maximum value squared. So this is capital D over little d squared over d. So see that? Okay, all right, so how much does that look like? This is 2 pi over L. I can pull out capital D over little d, so I pull that out. Then I have R0 plus d over 2. Okay. So that's my number of pits. I found the number of pits in my DVD disk. All right. Now what do I know here? What's really going on physically? These pits here are separated by a distance d. let me plot it out this way. This might look more familiar. That's a pit. The next pit on the next concentric ring it acts like n slits. Each pit is a slightly bent thing. It acts like a slit. It light reflects up and so on and so forth. So I send light, distance d between these slits. I send light of wavelength lambda. I see a pattern on the screen of diffraction. Okay. And when would that happen? The pattern, how does the pattern look like? This is I total on the screen divided by, let's say, the angle on the screen or something. It has a central maxima where all the things just go to the center, the zero path difference. And then it looks like there are a couple minimas, again a maxima, a couple minima and so on and so forth, a couple minima, and another maxima and so on and so forth. Okay. So this is the 0th order maximum. These are the first primary maximums. Okay. And when you think this might happen, at what condition would you get the first primary maximum? In the double slit experiment, where you just have two slits, when the two slits are in phase, that the path difference, let's say, is a wavelength, then they are conjunctively interfering, right? So if successive slits are differing in paths by lambda, it will be constructive. And successive things differ by d sine theta. Just like before, two slits, angle theta, path difference is d sine theta. So whenever d sine theta is lambda, you have to have a difference. So I don't know what d is. I mean, we just have this. I don't know what d in the DVD cases. I can't go and look at the disk and can someone see the d's? I can. So that's one thing. But what you can measure by looking at the disk, you can measure R naught. Take a ruler, look at the central hole, some centimeters. I think I got numbers somewhere. So I did this last night, and I found R naught to be 2.1 centimeters. I found capital D, the writable part of the disk, to be 4.3 centimeters. I looked up the disk manufacturer, looked up online, average D. On average, the distance between these, so this was the D, as I wrote down. The L between the pits, this L is around 800 nanometers. That's how the manufacturer makes it. He makes these pits in these tiny distances. Okay. Again, this is a very, very crude approximation. I made the spiral into concentric circles. I have an average value of the pit. Actually, the pits are really complicated, but this is a really simple model. Okay. So I have the value of capital D. I have R naught. I have D. I have F. I don't know little d. I don't know the distance between the grating of the slits. But I know the fact that d sine theta is lambda for the first primary maximum for this peak. I can go and measure that. Okay, so let's do that and see what we get. Okay, so I got like tape and stuff to do a good job, but I think I'll probably skip that because there's not enough time. So this tape thing here says, it's an old tape dispenser, and like this yellow paper on top that says, I belong in room 441 Lauritsen, do not take me away or you die. If something happens to me, you know what happened. Anyways, tell mom I loved her. Okay, so now what do you expect? When you shine light through the slits, it goes through the slits, right, and has a diffraction pattern. For the disk, they have a reflective coating here, and therefore it won't go through, it will reflect back. So I expect the pattern to be back here itself. Okay? So I would request everyone to gather around. Maybe hold on. Maybe see how you should want to get rid of the camera. We don't have your faces in the camera, so let's keep it safe.
Bye.
Or
How do
what can
you
we do?
detach this?
Or you know what? You just work from there. Can you all like kind of come around me and you can try not to have your faces in there. But if they do come in, we'll blur them out. Don't worry. we will blur it out. It's not possible to do it that way. That's fine. So now the gratings are going this way, right? And so this is how the D's are separated out. If I shine light, I expect a pattern this way. Let's see how. So I'll put this here. And I hope this works. Do we see the pattern somewhat? I'm going to hold this here and punch it. Maybe around here. Okay. Can you come out there? Okay. Alright, so see this? That's the first primary maximum. You'll see it? See, how do you see it?
I do.
Okay. Can someone measure this angle? This will be a crude estimate, but we can get a sense. 60?
60.
It's a good angle.
Yeah.
60?
Yeah.
Alright, we keep it. Everyone convinced? We all see it? See the diffraction pattern, right? And the angle that the incident light makes with the diffraction, the first primary maxima, this angle we found to be 60 degrees. Okay? Thank you so much. Let's get back to the board and see what we find. So we found theta, where it's maximized to the first maxima, to be 60 degrees. Okay? Therefore, what's sine theta? That I remember from this. Right? D sine theta is lambda. So D is lambda over sine theta max. And this laser, the wavelength is red light. The laser says it's 650 nanometers. If you don't trust me, you can come and have a look. Right? Usually don't lie. So this is 650 nanometers divided by square root 3 over 2. Can someone give me a number for this?
750.
750 nanometers. I found little d. I know L from the manufacturer. I know capital D. I know R naught. I know capital D. N bits. How much is n bits? 2 pi over L is 800 nanometers, so 10 to the minus 9 meters. D is 750 nanometers, so 750 nanometers, so 10 to the minus 9, times capital D was 4.3 centimeters, so 4.3 into 10 to the minus 2 meters, divided by little d, which we already have, times R naught is 2.1 into 10 to the minus 2, plus capital D is 4.3 into 10 to the minus 2. So this is 2 pi over 800 times 750 times 4.3 times 2. This is 5.4. There's also a 2 here in there. So 2.1, 2.1, 4.2 times 10 to the minus 9, minus 18 goes up, it's 18. 18 minus 4 is 16. How much is n bits? You're almost done, sir. I don't have numbers, so I trust you folks.
1.9 times 10 to the 10.
Okay, 1.9 times 10 to the 10. Number of bits in the disk. Now let's assume, or which is a reasonable assumption, that every one bit holds one bit. If one bit holds one bit, how many gigabytes does this have? So number of gigabytes is n bits. 8 bits make a byte. And I'm going to do the giga thing, so 10 to the 9. How much is that? 1.9 divided by 8.
2.4.
The whole thing, 2.4?
I think so.
I think that sounds reasonable. It's a 4 GB disk. By the crudest approximation, I got 2.4 GB. That's not bad. If I could even get the GB part right, I'm happy. So diffraction interferences are not fantastical elements. These are real life things. We use it every day. So I hope you enjoyed this. Thank you all for coming. Hope you'll have a good break. And I'll see you next Wednesday. And yeah, take it easy.